The last lesson of this unit. Review day next class, test on Friday for UA Dayers. We're going to examine this type of function. It's called an accumulation function. Okay? And notice what this accumulation function looks like. We have some function is equal to the area from 2 to a variable under another function. And we'll see how those two functions are going to be related in a little bit. But for right now, we're just going to think of it as this. This is an example. And in general, we'll say some function equals the accumulated area from a value to a variable, any variable, x, of another function. Okay? So it's really like this piece of it is the accumulation part. We'll find out that G and F are related, if this is true. Or G and the area from 2 to F are related. Okay? Well, let's look at this graph. This is the graph of F. It's important to see what we have. And in this case, I have the graph of F. It could be the graph of F of X, but in this case, we have, we can have T here, and it's a graph of F of T. Okay. Could you find G of 4 if G of X equals the integral from 2 to X of F of T dt? What would you do? That's exactly right. So G of 4 is right here where X is. So if I wanted to find G of 4, wherever I see X, I'll just replace it with 4, and I'll find the area under F from 2 to 4. And what is that? Here is F. The area from 2 to 4 is 4. Okay, we can do the same thing for G of 7 and G of 2. If I wanted to find G of 7, I would just replace 7 for X in this accumulation function. And then say it'd be the area from 2 to 7 under F of T dt. 2 to 7, this is an area of 1. This is an area of -2, so 3. Notice 7 is where X is. X and X. And then finally, what would G of 2 be? 0, because it's the area from 2 to 2. Okay. Now, notice how this should make sense if we're just plugging in X's, but this value down here, this value could change, okay? If this was, 4 or something, all of these answers would change. This would be the integral from 4 to 4. This would become 0. This would be the area from 4 to 7. 4 to 7 would be -1. And this would be 4 to 2. Now we'd go from right to left, 4 to 2. 4 to 2 would be -2. -4. Okay? So depending on this number, all of these values can change. Okay? So that's what we're going to start with. We're going to start with finding, the values of G of this value if it's equal to this accumulation function. So we started with finding the values when we're given a graph. What if I'm giving you a function? Like this. What if I say g of x is equal to the integral from pi over 6 to x under cosine t dt, or the accumulated area from pi over 6 to whatever value of cosine t? Could you find g of pi over 3? The answer is yes, and why don't you guys go for it? Now, we don't have our calculator. Our calculator really won't help us here. So we need to apply the fundamental theorem of calculus, which just says this area is going to be equal to the change in the antiderivative. Okay, so to find g of pi over 3, that's going to be this. So I have to now find the change in the antiderivative to find that. Okay, so it's all kind of review. It's all stuff we've done. It's just this looks a little different. You know, we just have to plug in a value first. Sine of pi over 3, root 3 over 2, sine of pi over 6, 1/2. Okay, so root 3 minus 1 over 2. Questions about how I did that? I want to find a value for g. I can just plug in that value for x and then go for it. Okay. Well, the next question is, what is the derivative of that? And this is where the second fundamental theorem of calculus comes into play. Okay, so what is the derivative of this accumulation function? This area from some value to some unknown variable of f. And I'm going to do that kind of going through the previous problem, the previous example. And then if we could do it for this one, we might be able to get the general form of this any function from any value to x. Okay? So I'm going to take the derivative of this. Now, I don't know how to take the derivative of an integral from this to this of cosine, so I'm just going to kind of work on the inside first. And I'm going to take the derivative as my last step. So I'll say, all right, I'm going to take the derivative of this. Well, I'm going to use the fundamental theorem of calculus and say, okay, the area under the curve from pi over 6 to x is going to be the change of the antiderivative. And then I'll even go a step further because I don't like this line. I'll say, okay, I'm going to have to take the derivative of, I'll plug in x for t because that's like f of b. And I'll subtract the sine of pi over 6. Okay, well now I can actually take the derivative of what I see. So I can now do the whole take the derivative of this integral thing. I get this. So question is, what is the derivative of sine? Cosine. What's the derivative of sine of pi over 6? Well, sine of pi over 6 is negative, or is a half, and it's minus a half. What's the derivative of a half? 0. So it turns out the sine of pi over 6, the derivative of that is just 0. So this is just cos x minus 0, or just cos x. Well, we started with the derivative of this integral from a value to x of cosine t, and we ended up with cosine x. Well, maybe before we jump and talk about in general, what if I changed, what if I changed this pi over 6 to, what if I attempt to change the pi over 6 to a pi over 2? Would it matter? No, because it would just be the sine of pi over 2, which is just a value, take the derivative, it would just be 0. So even if I chose to use 0, this would still be 0. So it doesn't matter what this value is. It could be any value. I'm still getting cosine of x. Okay? Well, think about it. If I want to find an area, I find a change in an antiderivative. So I take the antiderivative. Well, you want to take a derivative of an antiderivative. What happens? You go back to where you started. So if I want to take the derivative of this, it's just whatever's on the inside, only with x's instead of t's. Okay, the second fundamental theorem of calculus is really saying that the derivative of an integral is just whatever you have. It's almost like you take the derivative of an antiderivative and you get back to where you start. Well, it also means something else, and I guess we'll get to that later. So we could do a quick example, like a question you might see on your homework. What is the derivative of this? So derivative of the integral from negative 12 to x of the square root of t squared plus 1. So we really can't find that antiderivative, so I can't really go through all the steps that I did with that cosine function. But you got to just think about it. I'm going to, if I wanted to find out what this is, I'd have to take the antiderivative of it, plug in x, and then I'd have to take the derivative of that antiderivative. What do I get? Whatever I started with, just with an x. No. Right? Because a squared plus b squared does not equal a plus b squared, right? So, but that's the answer. You don't even have to simplify it, okay? So that's good. This is good. So we know how to take the derivative of this funky function, which, you know, we can evaluate values for. All right, well, what if we have some crazy stuff up here? What if it's not just x? What if it's x cubed plus 2? And I don't want it to be x cubed plus 2. I want it to be x to the 5th plus 2. And I want this to be 3t squared plus 1. dt. Right? The hope is that my answer, by going off of what we discovered earlier, the hope is that the answer is 3 times x to the 5th plus 2 squared plus 1. Right? Well, let's find out. I'm actually going to do this one step at a time because I can, and we'll be able to see if that's our answer. All right. So I'm going to take the derivative of the inside. Let's work through the inside first. I'm just going to go ahead and use the fundamental theorem of calculus to say I'll be taking the derivative of this antiderivative and the change in it between negative 12 and x to the fifth plus 2. So that's t cubed plus t evaluated from negative 12 to x to the fifth plus 2. All right, let's plug that in. I'm going to be taking the derivative of x to the fifth plus 2 cubed plus x to the fifth plus 2. I need to move this down. Okay, minus negative 12 cubed minus 12. Okay. I'm now ready to take the derivative of this stuff. So my hope was that the answer is just 3x to the fifth plus 2 squared plus 1. Well, if I take the derivative of this stuff, am I going to get this? Let's find out. The derivative of x to the fifth plus 2 cubed is 3. X to the fifth plus 2 squared times the derivative of x to the fifth plus 2, 5x to the fourth, plus the derivative of x to the fifth plus 2, 5x to the fourth, plus the derivative of all this, which is just 0. So I end up with this as my answer, which is not this, unfortunately. But it's close to this, actually. Let's go back, maybe. Let's not cross this out so quickly. Watch how I can rewrite this. This is 3 times x to the fifth plus 2 squared plus 1, all being multiplied by 5x to the fourth. Right? So I started by wanting to take the derivative of this really, really nasty accumulation function with a function in a bound, and this is what I got for my answer. So I'm close to my guess, which is just plug in x to the fifth plus 2. But what do I have to do after I plug in the x to the fifth plus 2? Multiply it by the derivative of whatever this is. So in general, this is f of g of x. Now this is really important. It's this quantity times g prime of x. Okay? So if there's multiple things in this f of g of x, you got to put that in parentheses and multiply by g prime of x. Okay, now this is like, oh yeah, it's like the chain rule, right? But it's not the chain rule. Chain rule is like you take a derivative of a composition of functions, you get f prime of g of x times g prime. This is not the same as the chain rule. This is applying the chain rule, but this is kind of its own rule. This is the derivative of an accumulation function with another function in a boundary. Okay? Application of the chain rule, not the chain rule. Not the same as the chain rule. Okay. So now that we know this rule, we don't have to do all this messy stuff that I did. And there will be some situations where you can't do what I did because, like that first example we did, you don't know how to take the antiderivative of the square root of t squared plus 1. You just have to know the rule that, I'd be taking the derivative of the antiderivative, boom, I get what I started with x's. Well, This one you could go through the messy stuff, but let's see if you could just find the derivative of this without doing the messy stuff. And just applying the rule that we just discovered. It would just be the derivative of the antiderivative of this, which would end up back where we started, with that plugged in, but multiplied by the derivative of that, which is where our chain rule kind of comes into play. Now, important, what if this was cos t plus 1? Or cos t plus 1? Let's do that. Cos t plus 1. The answer would be cos of x cubed plus x cubed plus 1, not times 3x squared like that, but the entire thing times 3x squared. Okay, you'd have to distribute that 3x squared in. So write that down as a second example if you need to. What about this? You don't know what the antiderivative of e to the t squared is, but you could tell me the derivative of the area from 5 to x cubed of e to the t squared by applying the second fundamental theorem of calculus. You want to simplify a little bit, you can. 3e to the x cubed times x to the 8th after some simplification. Okay, cool. Well, what if we had variables in both of our bounds? Anybody know how to tackle this? Mr. Barron? Exactly. Perfect, perfect, perfect. Why aren't we doing that for all the other problems we've done? Why do we have to do the subtraction? Exactly. Whenever we had a value here, we would be plugging in constants, and we'd be taking derivative of constants, which is 0, which is why this whole minus thing went away. And that's why this whole minus thing went away. And we ended up with just the derivative of this. Well, if I had x's in both, it would just be, you know, the same rule that we're doing, just for the top, minus the same rule for the bottom. So I can write the general form underneath it, and then we'll do the top one together. if we want to take the derivative of, g of x to h of x of f of t dt, it would just be f of h of x, that guy on the top, times h prime of x, and then we'd have minus the derivative of big F of a, which we would say is f of g of x, times g prime of x. Okay? Usually this is gone because g of x is a number and the derivative of the number is 0, but in this case this is going to have x's, so that's why we have to include it. Okay? So let's see what we'll have here. You guys could do it. I'll do it as well. We can compare our answers. Questions about that? Notice how I'm using the parentheses around my entire function times this derivative. Entire function times the derivative. Okay. Well, here's the connection between g and this accumulation function. If I said g was equal to this, how is g related to f? Or how is g related to this accumulation function of f? I won't say f. How is g? G is what? It's fg over time. No. What if I took the derivative of both sides? What would g prime equal? What's the derivative of this? Just f with x's. Aha. Okay. So, what if I went backwards? G would equal the antiderivative of f. What if I went like this on both sides? I would get g is equal to big F. Turns out this is how you could write the antiderivative of f. I could take g and actually replace it with big F if I wanted to. This is another way, this accumulation function is another way to write the antiderivative of f. Of course, I'd have like plus c's here, right? But don't worry about that. Okay? Now, I don't like this big F. I feel like it's confusing. I almost like to think of them as being different. And most questions will not use big F. They will use G. So if that's starting to get confusing to you, don't worry. treat it as two separate things, and you'll actually be able to understand these problems better. But what's great about that is that if I asked you to write an expression for the antiderivative of e to the negative x squared sine x. You'd be like, well, Mr. Messer, I can't find that antiderivative, but I can just cheat and say, oh, here's an antiderivative expression. 0 to x of e to the negative t squared sine t dt. That would be an expression for the antiderivative. The accumulation of the area under, and if we could figure out what this was, you know, and actually be able to graph it, that would be the actual antiderivative graph. Okay, we're almost going backwards. You know, like we're taking derivatives of these areas where we were just kind of finding the areas by using these antiderivatives. Now we're taking derivatives of the antiderivatives. It's going all over the place. Okay, but what is going to be done with these accumulation functions is we will have to kind of be able to analyze this G and what's going on with G given F. Okay, we will be given situations like this, where I say, okay, G is equal to the area from 0 to x under F. This is F that I'm giving you. And then all of these questions from Unit 4 are going to start repopping. Like, when does G have a relative extrema? Or when does G have an inflection point? And you will have to be able to use your knowledge of the second fundamental theorem of calculus to connect G with this, and to get information from the graph of F to tell you about what's going on with G. Okay, it's going to seem complicated, but it's really not. Okay, here's why. If I start with G, and I know G is equal to the accumulation function, when I take the derivative of both sides, we understand that G prime is the same as just F. I can go another step and take the derivative of this side and say G double prime will be equal to F prime. This is very, very important. The most important thing from this lesson is this kind of step down process. G is the antiderivative of F. G prime is F. G double prime is F prime. They're like one away from each other. Okay? And we also need to remember our stuff from Unit 4. Okay, we need to remember what we have to do to see when something's increasing or decreasing. So we can tell when any function, whether it's an F, a G, an F prime, a G prime, Q double prime, we can tell when that is increasing or decreasing by analyzing what? Yeah, we're going to do that, which is good. How do I tell when something's increasing or decreasing? I'm going to analyze its derivative. Okay? But first, we're going to analyze it by finding when the derivative is 0, and then we'll be able to do these situations where if we know our zeros, we can say, oh, positive minus positive. This is for the derivative. And if it's positive, that means my original function is increasing, my original function is decreasing, and my original function is increasing. I can then tell if we have a max or a min. A max or a min is when the derivative, we'll talk about the max first. Changes sign from positive to negative. That's a max. A min occurs when a derivative changes sign from negative to positive. That'd be the location of a min. This is all stuff from Unit 4, just reminding you of it because we're going to be using it again. How can we tell when a function is concave up or down? What do we analyze? Second derivative. If it's positive, we're concave up. If the second derivative is negative, we're concave down. Now, I'm going to ask you, when is the graph of f prime concave up? Would you look at the signs of f double prime? You'd have to look at f triple prime, right? Because you'd analyze the signs of the second derivative of f prime. That's when it starts to get a little bit confusing, but that's why I'm not using f or one specific function. I'm using, any function, analyze its derivative. It's going to tell you if it's increasing or decreasing. Any function, analyze the second derivative. You'll see when it's concave up, concave down. Okay, inflection points, that's when the second derivative changes sign. Okay, so what's going to happen in these problems is you're going to have information for f. But you will be asked questions about g. So you have information for f, and you're going to be asked, when does g increase? And you know from Unit 4, you're like, oh, g increases when g prime is positive, right? But you don't have information about g. You have information about f. So what is the information you will use from f that will tell you when g prime is positive? When f is positive, g prime is the same as f, so we will figure out when g prime, which is equal to f, is positive. Does that make sense? If I'm asked when does or when is g concave down, well, you know that's when g double prime is negative. You know that from Unit 4. But now the extra step is you need to connect that g double prime is the same as f prime. And we will look to see when f prime is negative. Okay? Let's do a couple quick problems. Just so you're comfortable being able to find g, g prime, or g double prime given information for f. And once we can do that, we'll start doing like the more open-ended, when does g have a max, min, increase, decrease. Okay? So here's the first set of problems. G is equal to the integral from 4 to x of f. Find g of 3, g prime of 3, and g double prime of 3. Compare your answers with the neighbor. I'll do the first one. G of 3 is the area from 4 to 3 under F. From 4 to 3, this is 1 by 2. That's a positive 2 from left to right. It would be negative 2 from right to left. Find G prime of 3 and G double prime of 3. Check with a neighbor. I need more people checking right now. The key is this. We have this written down. We can figure out the answer for G prime of 3 and G double prime of 3. I'll write it down here. G prime is just equal to that. G double prime Yep. It does for the first one, for sure. The other ones it doesn't. Yep. So G prime is equal to F of 3. F of 3, you just look at the graph. Above 3, we get the y coordinate 2. G double prime is equal to F prime of 3, which is 0.
So the graph of F is X and F T is the same?
Yes.
Okay.
Now, be quiet. I'm going to go through this problem even after the bell rings. I want you to see this problem, and then there'll be maybe like 2 or 3 more problems on the video, okay? So, here's a typical problem. I give you the graph of F, and I tell you G is equal to the accumulated area from 0 to X under F. First question is G of 3 positive, negative, or 0? Well, I look from 0 to 3, it's going to be negative. This area is negative. Okay, so we got that first one. Part 2, what is G prime of 3? Well, I know G prime is going to be the same as F. F of 3 is 0. Hold on, 2 more. When does G have relative extrema? Well, I'm immediately thinking unit 4. G has relative extrema when G prime changes sign. G prime changes sign when? When F changes sign. When does F change sign? At 3. Right here, when X is 3, would we have a max or a min for G? It's a min. F goes from negatives to positives. Do we see that? The function values for F go from negatives to positives at 3. When does G have an inflection point? When G double prime, which is equal to F prime, changes sign. When does that happen? F prime goes from positive, it's the slopes of F, to negatives to positives, 0 and 2. Thank you. Couple more problems on the video. Okay, couple more. Here's F. We're told G is the area from 0 to X. Now this number does matter for the first guy, G of 2. We're going from 0 to 2. So that's the area here plus the area here. It appears that this is 0. Don't have to calculate it. I can kind of visually inspect. Second one, G prime of 2. Well, that's going to be the same as F of 2. F of 2 is negative 4. G double prime of 2. That'll be the same as F prime of 2. f prime of 2 appears to be 0. Okay? When does G have relative extrema? When does G have inflection points? Well, G will have relative extrema when G prime changes sign. G prime or G prime, which is equal to F, changes sign. Well, F changes sign only once. It has 1, 2, 3 zeros, but it only changes sign when X is 1. So, X equals 1 is our only relative extrema. It is a max because F goes from positives to negatives from left to right at 1. Inflection points when G double prime, which is equal to F prime, changes sign. So that is looking at the slopes of F prime, I'll be able to figure out the concavity of G, or the signs of G double prime. So the slopes of F or F prime are negative until we get to 2, then they're positive. Until we get to 3, then they switch back to negative, and then at 4, they go back to being positive. So I would say there is 1, 2, 3 inflection points at 2, 3, and 4. More questions. Given F prime is equal to this, when is f of x increasing, decreasing, concave up, concave down in the interval from 0 to 6? Well, this is tough. F is going to be increasing or decreasing when f prime is positive or negative. Now, how do I know what f prime is doing if it's equal to this? Well, it's not going to be that bad. Maybe if we look at f double prime will be equal to the derivative of this, which would be x squared minus 4x. Okay, so let's at least start with the concavity question where I can find when this changes sign. How do I figure out when x squared minus 4x changes sign? You first start by finding their zeros. So I set this equal to 0. I figure out that when x equals 0 or 4, we're going to change sign. So then I look at the signs of f double prime around these to see when we're concave up or down. So to the left of 0, it's going to be a negative and a negative. That's a positive. Between 0 and 4, we'll have a negative. After 4 will be positive. So this is when we're concave down. So f is going to be concave down from 0 to 4. It's going to be concave up from 4 on. Now, when is f increasing or decreasing? Well, you know, the best thing I can think of doing is to graph t squared minus 4t. So let's look at that. If I graph t squared minus 4t, I'll start by maybe setting it equal to 0, t minus 4. We already did this, so 0 and 4. So this is the graph of t squared minus 4t. And this is another way you can see how the values are telling me the concavity. Well, now we're talking about the area from 0 to x under t squared minus 4t. Well, no matter what x is, no matter where x is between 0 and 6, well, not between 0 and 6. Probably should be between 0 and 4 to make this question fair. Because my area here is all negative. So I'm just going to be continuing to decrease if I'm continuing to add negative values. No, it's fair. But then from 4 to 6, I'm adding this positive area. So I'd be increasing values there. I'd start at 0. I'd be going down because I'm accumulating negative area. And then I'd be going up because it'd be positive area. I have to think about that. Yeah, Yeah, we'd be continuing to accumulate negative area from 0 to 4. So no matter what value I'm looking at, for f prime is always going to be, oh, no. Yeah, it looks like we're going to be decreasing everywhere. Because f prime is always definitely negative everywhere from 0 to 4 for any value. F prime at 5 and 6 and around 5 and 6, f prime would probably still be negative because this area is more negative than this area here. So since I'm looking at f prime, I think that we're going to be decreasing everywhere on this interval because all of the f prime values until this area here from 4 to 6 is equivalent to the area, or from 4 to whatever is equivalent to the area from 0 to 4, then we still will have negative f prime values, and since we'll have negative f prime values, we will be decreasing. Okay? Interesting problem, very interesting problem. Let me actually calculate the area. Math 9, t squared minus 4t from 0 to 4. That is negative 10 2/3. If I do the same thing, four to 6. Whoa, from 4 to 6, it's actually the same. So all the values are going to be negative until we get to 6, and that's when it's going to be 0. So from 0 to 6, I would say here, yeah, it's decreasing. Okay, the concept should make sense. It's like f prime is going to be the accumulated area. It's all going to be negative until we get to 6. For the concavity, we analyze the signs of f double prime. We are concave down until 4. We are concave up after 4. Okay. Next problem. We got g, and we're asked when is g of x concave down. Okay. G of x is going to be concave down when g double prime is less than 0. So I got to get to g double prime. Well, g prime will just be this with x's plugged in. G double prime will be the derivative of this. So that's 6x squared minus 30x plus 36. I'm going to figure out when this is concave down, so I got to figure out when this is negative. To figure that out, I'm going to set this equal to 0 first, and then analyze the signs around those. So 6 goes into all of these, so I'll factor out a 6. X squared minus 5x plus 6. I'll factor this. 6 times x minus 3, x plus 2, x minus 2. That gives me x could equal 3 and 2. Okay, so that's when g double prime equals 0 at 3 and 2. So to figure out when it's positive or negative, and especially when it's negative, we will analyze the signs of g double prime by plugging in test values like 4, it's a positive, like 2.5, positive, negative, positive, negative, like 1, positive, negative, negative. That's a positive. So when is it concave down? Between 2 and 3. Good question. Okay. We will go over more questions like these in the future. This is an AP style question. It's a full AP question, all based off of this accumulation function and, you know, questions about when we have maxes, mins, et cetera, et cetera. So we will go over problems like this for the review day. All right, thank you.